All right. Hello, anatomy people. Here to continue with our discussion on blood. So, um, if you have completed the first video, we know a little bit about the components of blood, the formed elements, the plasma itself. We talked a little bit about hematocrit. Now we're going to get very specific into the process of blood formation, what we call hematopoiesis, and very specifically, we're going to look at the erythrocytes in this video. So we begin with hematopoiesis, or some people call it just hemopoiesis. This is the process, the maturation, the developmental pattern of blood formation, basically. So it will occur in the red bone marrow. And if you've ever heard of a term, a stem cell. So stem cells are, they're basically cells that have no direct instruction yet. So think of some of your fellow students, your fellow peers. They start at EPCC or whatever, wherever, and they don't know yet what they're going to study. They just kind of go with the flow, see what they find interesting. Others, by the time they sign up for the first course, they already know what they want to do, right? They've already sort of been programmed on what they're going to do. So when we look at blood formation, we're going to start with a type of stem cell. We're going to call this the hemocytoblast. So over here on the far left, right? Hemocytoblast. Hemo meaning blood, cyto is cell. And if you remember from last semester, blast is the opposite of a clast. A blast is going to be involved in the metabolic process to form something. Clast is a degradative sort of process. So blast, a cell that will form blood, basically. So the hemocytoblast. Now we say it's a stem cell, but it's not a total blank page, right? So by the time that this hemocytoblast has developed, it is already committed to becoming one type of blood cell. So a true type of stem cell wouldn't be committed that way. It could become a muscle cell. It could become a liver cell, a kidney cell. So again, a hemocytoblast is a type of stem cell that's kind of flexible and can become multiple types of blood cells. So I hope that makes sense. So all blood cells are derived from a single population of stem cells called hemocytoblasts. So I hope you start to see the significance, the importance of this hemocytoblast. Without hemocytoblasts, we have no ability to form any of the blood cells, any of the formed elements. So just kind of looking here at the pathway, right? So the stem cell, because of certain signals, because of certain hormones, certain cellular factors, now becomes committed to becoming a red blood cell. So it's signed the letter of intent. I'm going to become a red blood cell, yeah? And basically, there's a process that happens. We shift from a pro-erythroblast to an early erythroblast, a late erythroblast, a normal blast, and right here, I want you to kind of look at this part right here. Hope you see this is kind of weird. We say this is the phase of the nuclear ejection. So we're getting rid of the nucleus at this point, which leads us to the reticulocytes, and then finally our erythrocyte. Erythrocyte, fancy way of saying the red blood cell. So again, let's look at this. So erythrocytes, again, are biconcave discs. So imagine like some of those, what are they, the little candies? I think they're Smarties, I think they're called. They're like little sugar candies that they're kind of collapsed in from the top, and then they're kind of collapsed in from the bottom, right? I think they look very similar to these erythrocytes. The candies have a real sharp edge. Erythrocytes don't, which is going to make it easier for them to kind of navigate through these blood vessels. Now, if we look at the idea of, well, why, right? Why is it biconcave, right? It didn't start biconcave. It started like a round cell. But don't forget what happened here. We kick our nucleus out. So the nucleus is a very important part of all cells, if you remember from 1306. So we kick the nucleus out, and then that cell kind of deflates down upon itself. So this is going to have major significance, right? So we kick that nucleus out, other organelles get kicked out, and we have basically this empty, deflated membrane, cellular membrane with no organelles. And this has major significance. If you don't have organelles in the cell, there's no nucleus, there's no Golgi apparatus, no endoplasmic reticulum. Well, that cell doesn't have the ability to regenerate itself if it gets injured. So because of that fact, because of this phase 3, because we kick the nucleus out, that causes this cell to be very short-lived or short-lived. Right? So important, right? So basically it's a pouch of cytoplasm, of fluid, and in that fluid is jam-packed with hemoglobin, which we're going to talk about shortly. Right? So hemoglobin. And there's some ranges for you nursing types. So normal ranges for females, normal ranges for males, right? But just looking at the idea of erythrocytes, red blood cells. So we say they're basically pouches of cytoplasm filled with hemoglobin. Right? Hemoglobin is a critical. It's going to be a protein. It contains the globin, right? This protein, the globin, is going to be involved in the transport of gases. So primarily oxygen, but also carbon dioxide. Hemoglobin consists of basically 4 parts, right? 4 globin chains. Globins are a fancy way of saying polypeptides, which is a fancy way of saying protein. So there are 4 protein chains, all these weird sort of convoluted protein chains. And within the center of each protein chain, of each globin, we're going to have a heme. So 4 protein chains, each one has a heme. So we have a total of 4 hemes. In the center of each heme, we have an iron. So I think you've heard a little bit about requiring iron for normal blood functionality. Well, this is the role that iron plays here, right? Within the hemoglobin itself. Again, there's your ranges of hemoglobin, females and males. But let's look at that important hemoglobin molecule. So 4 globins. So here we have like a brownish globin. Here we have a lighter brownish globin, another globin, and another brown globin, right? So 4 of these polypeptide chains, and in the center of each chain, we have this little red disc, that red disc being the heme, and in the center of the heme, we have Fe, that element we call iron. So that iron is where we actually have the chemical reaction that allows oxygen to bind. So oxygen would directly interact, bind with that iron. So one hemoglobin has 4 hemes, 4 iron centers. So thereby one hemoglobin can transport 4 oxygen molecules. So that's an important sort of little statistic there that you're going to need. So I hope that's making sense so far, right? Our little deflated cell, little pouch of hemoglobin, basically, right? So understand that these red blood cells are active, right? They do a lot of work. They're flowing through the body, transporting oxygen, transporting carbon dioxide. But they have lost their ability to regenerate. They have lost their ability to repair, to, if they get a little bit dented or damaged, they can't fix themselves. So because of that, they have a relatively short lifespan, right? So 3 to 4 months, we say, is their lifespan, depending on how active, how much, effort that person is exhibiting, how much wear and tear these red blood cells are having to go through. But if we're losing red blood cells basically constantly, right? Each one lives only about 3 to 4 months. So on a daily basis, you can imagine we produce around 100 billion new cells each day, right? 100 billion new red blood cells each day. Hope you understand that that's a lot. And I don't know, maybe some of you haven't really done much today. You've just been sitting around and you say, man, I'm tired. I haven't done much, but I'm tired. Well, man, you just made 100 billion new red blood cells. So I understand why you'd be a little bit tired, right? So that's a lot of work for the body to constantly have to regenerate these red blood cells. So how does this happen, right? So we have to have some sort of feedback mechanism. We have to have some way of monitoring and sort of generating the instruction for new red blood cells. So where does that instruction come from? Right? We think, well, maybe it's coming from the blood vessel itself. No. Maybe it's coming from the heart. No. It's kind of a weird spot, right? It's coming actually from the kidneys. So the kidneys are in direct sort of interaction with the blood each day, right? Constantly throughout the day, they're filtering, they're kind of monitoring what's going on, what the composition of the blood is. So the kidneys take on the role of producing a very important hormone that we call erythropoietin, right? Very important. I would know this on for the exam if I were you, right? Erythropoietin. So very, very important hormone that basically is going to generate the formation of new red blood cells. So as red blood cells start to decrease in the body, the kidney kind of senses, man, we don't have enough red blood cells. It releases the hormone. The hormone goes and causes the red bone marrow to stimulate production of red blood cells. I hope you remember what important cell gets stimulated. It stimulates which cell? Yeah, did you say hemocytoblast? I hope you said hemocytoblast. So those are the cells that then start committing themselves to form red blood cells in response to this hormone erythropoietin. So erythropoietin, or sometimes we just call it EPO, erythropoietin is going to be produced by the kidneys, right? It's going to be produced when there's what we call a hypoxic situation. Hypoxia is a low oxygen carrying capacity by the blood. You got to be a little bit kind of careful when we analyze this, right? So produced when there is a low oxygen carrying ability by the blood. So everything can be perfect, but as long as the body senses that there's not enough oxygen being transported, that's when we start to release EPO by the kidneys. So when can this happen? If there has been some sort of trauma, some sort of hemorrhage, if you have a bad injury, you bleed out a lot of blood, a lot of red blood cells, the kidneys will kind of figure that out. Wow, there's a blood loss of some sort. So it triggers in the formation to regenerate these red blood cells. Maybe the blood cell count is fine. Maybe we have enough red blood cells, but there's insufficient hemoglobin, or there's improper hemoglobin. That then would also trigger the formation of new red blood cells, hopefully with correct hemoglobin levels at that point. And another natural situation is when we are in low oxygen environments, typically caused by high altitude, high elevation. So I don't know if you've ever gone to Rio Doce or Cloudcroft is even, higher elevation. You go to Cloudcroft and you start climbing stairs or you start hiking, you get out of breath a lot, right? That's because of the low oxygen pressure, and the body senses that as a lower oxygen carrying capacity by the blood at that point. So that would naturally trigger the release of EPO, which would stimulate hemocytoblasts, which would generate more red blood cells. So hope, again, all this is sort of making sense here. So I kind of go now to the idea of athletics. This was, again, a big part of my background. So one of the easiest ways to enhance body performance is to start training at high altitude. And so you remember doing a lot of work in Colorado, doing a lot of work in these high mountain areas. You never ever start training for a marathon or a big race at in San Diego or in Houston, right? It's just too low of elevation, right? So when we go up to high altitude, you're running, you're training, there's not as much oxygen, so your body's actually working double. Even when you're asleep, you're in a low oxygen environment, so your body is training to manufacture more red blood cells. Right? Some people mimic this. You could do this here in El Paso. Right? I've seen these sort of masks that reduce the amount of oxygen that's allowing in. There's these little tents that you can set up, and you sleep in low oxygen levels, and basically it's triggering that high altitude response where the body is just seeing, hey, there's not that much oxygen, so it starts to release more EPO, manufacturing more red blood cells. Before I get that, so why would this be a good response, a natural response to training? Why would we want to have more red blood cells? Remember, more red blood cells equals a greater oxygen carrying capacity. So the more oxygen we can transport through the body, the more oxygen it can provide to the muscles, the longer we can stay aerobic and not shift into the anaerobic phase, so we build up lactic acid and soreness. So again, this is a common response to high altitude training. Now, this is a natural situation. Leave it to athletics. Leave it to sort of individuals wanting to take shortcuts and do things a little bit faster, a little bit easier. And we get into this big idea that we call blood doping. Right. So blood doping. This is a picture of Lance Armstrong, kind of a little bit outdated at this point, but he was a Tour of France champion cyclist, yeah, and basically people elevated him. Oh, he's the greatest athlete of all time, and then they kind of found out what he was doing, and basically he was stripped of all his medals and his everything that he did. So Lance Armstrong was participating in something that we call blood doping. Blood doping is still going on today in various forms, I suspect, but they're harder to do now at this point, right? But in the olden days, right? In the olden days, let's say you go and you start training in altitude. So let's say today we train in altitude and we start building more red blood cells, more red blood cells. So in, let's say, 2 weeks, a doctor comes and extracts my blood. I'm basically like you donate blood, right? So I donate blood, but it doesn't go to anybody. It goes to a refrigerator. And that blood is going to have a higher level of red blood cells. Okay, and it's my blood, right? That if I'm training, I make more red blood cells. 2 weeks, I get blood extracted. That blood is, plasma is removed, and all we save is the red blood cells. Okay, so I go and train for 2 more weeks. My body regenerates those red blood cells. I go give blood 2 weeks later. That blood goes back into the refrigerator, and I continue doing this for a while, up until maybe the couple days before the big race. So then I go back to the fridge and I take those red blood cells that were my red blood cells, and I have those red blood cells infused back into my body. So is it technically illegal if I'm getting some of my own cells put back into me? It's that real fine line, right? So basically, by putting more red blood cells into my body, I am then able to have a greater amount of oxygen transport. And so that's the old way, right? It's the old-fashioned way, actual donating blood and having the red blood cells infused back into the body. Okay, what they're doing after that, we're not worrying about red blood cells anymore, donating blood. Now what was increased artificially was the, come back over here, EPO. So EPO now can be purchased, right? EPO is now sold in little vials. So athletes were getting a hold of this and basically now injecting EPO, which is a natural hormone. Our body naturally produces EPO. So again, it gets into that real fine line. Is this illegal if it's something that we naturally produce? So they were getting away with this for a long while. It's just trying to enhance the number of red blood cells. So what we end up seeing, this is what we should see right here on the top left. This is a normal blood smear. This is the normal array, the normal count of red blood cells that we're supposed to see. And you can see a lot of white area because that's going to be filled with plasma. If you remember hematocrit should be about 45% red blood cell, and equal amounts of plasma. So this is normal. If you look at this bottom right one down here, this doesn't look normal. It looks like there's too many red blood cells in there. And this, again, is going to be a condition that we call polycythemia. Polycythemia is basically a condition where we have abnormally high numbers of erythrocytes. So too many red blood cells in circulation. So it gives you the range there. But this is the one that I think it makes more sense. So we have a hematocrit of about 80%, almost twice the normal amount. So if we go back here we have about 45% of hematocrit. Over here in polycythemia, we have about 80% hematocrit. So most of the blood is filled with red blood cells, right? So a tremendous amount of oxygen carrying capacity. And you would think, man, these runners are going to win the race very easy, right? So, and some did. Some did very well. Some, when they were running, dropped dead of a heart attack. And like, oh, wow, what happened? Now let's start to analyze this polycythemic situation, right? If your blood is crammed with that much red blood cells, those many red blood cells, there's not much space for the liquid part, for plasma. So think of like syrup. Syrup doesn't have a lot of water, so it's viscous, it's very thick. So imagine trying to pump syrup through your veins, right, through your vessels. The heart would have to work tremendously hard to pump that thick, viscous fluid throughout the system. And again, if it was done too excessively, it could lead to major, heart attacks and other, major problems. So these athletes had to kind of, play with the system, cheat the system to a level that was reasonable, where they wouldn't have a heart attack, a level that was not super obvious when they were, analyzed and, blood tested later. So again, got really elaborate and a little bit sad that they took it to that level. So we can actually naturally do this, but it was taken to a level way beyond what is healthy. So I'll try to show you a video of Lance Armstrong and some of the stuff he was doing. But so again, this is a situation where we have too many red blood cells, polycythemia, excessive amounts of red blood cells. If we go to the opposite spectrum, right, there's some disorders, some conditions where we have not enough red blood cells. And it's going to be a generic term that we call anemia. You may have heard of somebody that's anemic. So what does it mean if they're anemic? Well, they don't have either the correct number of red blood cells. They're deficient in their normal homeostatic level of red blood cells, right? So the condition in which the blood has a lower than normal oxygen carrying capacity. Okay, what can cause this? We can have just low red blood cell numbers. So due to lacerations, due to loss of blood, there can be some hemorrhagic conditions. Certain insect venoms, reptile venoms can cause that hemorrhagic sort of anemic conditions. We can have destruction of the cells. So there can be a couple of ways that we can have low red blood cell counts. Now we can have normal blood cell counts, but we can have low hemoglobin. And the easiest way that we can become anemic in that way is if there's not enough iron in the diet. And we can get into these iron deficient type of situations. So people that are not eating healthy enough, and this might be kind of weird too. If you think of maybe grandma, right? Think of grandma and those old black cast iron pans that she used to use, right? Well, it's an iron pan. And you can imagine the pan itself is iron, so there's probably contact with iron directly with the food. So we normally see elderly people never have an issue with being anemic. Now today, in our modern day, we have these Teflon pans, and we have all of these high-tech non-stick type of situations, and we got away from that cast iron kind of pan, those big black pans, and we start to see the correlation with more and more and more types of iron deficiency anemias, right? So kind of interesting in that regard. Just something very simple in the kitchen of grandma that's not there in the kitchen of us today, maybe something like that. And then lastly here we have abnormal hemoglobin, and these are going to be linked to genetic conditions. So these are something that you would be born with, something that you inherit from mom or dad. Maybe you have heard of sickle cell anemia, where the blood cells start to break, they sickle, they the actual erythrocyte fragments and cracks. Thalassemias are rarer conditions. Thalassemias are not real common here in El Paso. You start to see thalassemias a lot in people of like Greek descent, maybe some of the islands off of Italy, but it's not that common here. Right? In fact, I've never heard of a thalassemic case here in El Paso, but maybe if you dive into the literature, maybe you'll find something. But genetic abnormalities, low hemoglobin or abnormal hemoglobin, and low absolute number of red blood cells. All three of those conditions can generate anemic situations, right? Not enough oxygen carrying capacity of the blood. Oh, and I don't want to get into leukocytes yet. So with that one, I'm going to stop this video. Gives you something to think about. Get knowledgeable on red blood cells. I'll see if I can find the Lance Armstrong video, and I'll post these up, and I'll work tomorrow on the leukocytes, right? So with that, you'll have a good day, and I'll see y'all next time.